So let's get started. So thanks for coming today. So let's see. So today we're going to talk about privacy. This is kind of a so like a gap lecture in between the sections on like dimensional reduction, and then the last section on so the graph analysis. So I think it's still an important lecture, and we'll get into this so soon. But your seventh homework was due today, and you're only gonna have one homework left. So great. So we'll try and get this out around Wednesday the 10th. You probably want these two lectures before you really start the homework anyways, and it'll be due kind of after, let's see, this I think is like the reading day, so hopefully it's okay to be due then. If not, pretend it's due earlier or something like that. But I'll give you slack until that day. And so you don't have any active homework assignments out now, but you should be working towards your final report on your project. That's we do in like a week and a half. So I'll talk more about we can have more of a discussion of what to expect in the report so next week. But you know, I met with so a bunch of you as groups, and I think most of you are pretty much on track. Great. Okay. So today we're going to talk about data privacy, and so the point of this lecture is to both expose you to kind of some of the things you may not have thought about that might be kind of, if you're using data, that you can sort of knowledge you can get out of the data that you might not expect, and also kind of and then also some ways to try to prevent this from happening, including ways which are used have like become standards in various areas. And so we'll do this by walking through a number of examples where people have released data in the past in various ways, and then some consequences of this. And this has led to kind of these evolving standards of what it means for it be like safe ways to release data. And so these standards have been evolving because, you know, there'll be an incident and then someone will say, okay, we can protect the data this way, and then another researcher figures out how to still learn unwanted information about the data in this way. And so then the policy is evolved. And some of these things have stuck, even though they're kind of ways to learn information around them. So I think it's kind of useful to look at the history of what's going on here. But like the second lesson is that, you know, part of this is not all the data you're probably going to have to get access to in your career will be properly protected. Okay, so if you end up working at like a large company like Google, they're collecting lots and lots of data from customers, and they have to, because their whole business model is based on is like 90% of their revenue, or maybe 80% of the revenue is from like selling ads, and they're effective at selling ads because they know the profiles of the users, and so and they know they know the profiles of the users because they've collected data on the users, right? So it's important that they have this data, but like, what is an ethical way of actually using this data. And so so I don't completely have answers to these questions, unfortunately, right? So so I can't say, well, if you do this, then it's ethical, and if you don't do this, it's not going to be ethical, right? So at some point in your career, you're going to have these choices that are, what's the right thing to do with this data? Is it ethical to try and do this sort of analysis on this data set or not, right? So so I think the most important so kind of lesson to think about is try and think if you were the so if you were the data point. So if you're doing analysis on some, on some customers or on data you've collected from users or people you've kind of, you have information, and if one of those data points would you think it's reasonable to make this this sort of analysis on it, right? There's no right and wrong answer. A lot of you will have your different views of what is ethical and what is not ethical on this, but so I can't kind of tell you right and wrong, but I want to ask you to try and think about this, right? If you're at least trying to think about the consequences, you're more likely to make more ethical decisions than to look back and realize you did something wrong afterwards, right? And so unfortunately, there are stories that happen in industry where people don't realize the consequences, and that leads to some rushing headfirst into trying to kind of get slightly better performance, but at the expense of something that they just didn't have in mind. Okay, so so one of the kind of the simplest kind of, or one of the questions is, if you're a company, so should I so release a public data set, right? So something that was very popular, like in like the early 2000s, was that these companies on the web were all of a sudden realizing they were collecting all this cool information that they hadn't been able to collect so in the past, but they may have had limited kind of people to actually do analysis on this. And one common thing to do was to try and pair up with researchers, say in a university, to try and have them help analyze the data. And they would do this by posting some data sets online. And so if you look at what you've chosen for your projects, a lot of them are from data sets released over 10 years ago, right? And this is because that's when companies were like, okay, I'm happy to put this online. I'm not so worried about it. And so there were these data sets posted online, and this helped. And then people would develop techniques, especially for those sorts of data sets, which in turn help the company without them having to pay for the most of the like R&D themselves. And so, but this has happened much less so recently. So the company, the social company, the internet company that releases the most data are the ones that have like these public interface anyways, like Twitter, right? So Twitter will allow you to get 1% of tweets, but only 1%. If you're a company, you can buy 10%, and this is part of their business model. But they don't let you access all of the tweets because of some of the kind of things you can infer from the data set. Also, it's just a large amount of information, hard for them to process, but all the tweets are essentially public anyways. There's not a public-private barrier between. There's not much of an expectation of privacy. Whereas someplace like Facebook, where there are these different boundaries of who can view your Facebook feed, the questions are more are like more unclear, and Facebook has been in the news a lot and kind of actually consistently since the start of the company about what is, what sort of data should they have access to internally and what sort of data should they not. Certain companies like Google puts up kind of a barrier between different groups inside the company. So if you're looking at, if you're using Gmail, you'll see ads in Gmail but the information gleaned from your emails should not, I think, are not used to generate the ads. They're only used, like, not the actual text of your emails, except maybe that particular email itself, but not your whole history of emails. Like, they don't keep that, and they don't allow information from Gmail to be used with things like search. So there are certain barriers inside the companies, and they don't have access to all of your data. From what I've heard, those standards are looser in a company like Facebook, right? And so, was the right decision? That's not for me to make. But it's kind of interesting to have these sort of things in mind. So one place that this has come up. So I've talked about these companies on the internet, and this has kind of been a newer issue. It's not a very regulated space either. So someplace where this has been regulated more is in like health data. So this has for a long time have lots of regulation. And I'll give, I won't go through the exact details of what those regulations are, but we'll see something which is pretty similar to what those standards are. But this was also not always the case. There have been, for instance, one example why you might not want your health records listed is so let's say you have like a history of like cancer. So for instance, you probably have what's known as like public data, which could be something maybe like your age, although maybe your age you don't want people to know either. So maybe your like height, your like zip code. These are things that probably don't affect the knowledge of your like health, and maybe you can determine from like other sources. This would be like useful for like your maybe your name falls in here. These would be useful for like your identifiers to say something about a survey. Who are the patients at the hospital? But then there are these other more so like this private data, and I'll just use an example like if you have a history of cancer, right? So it's possible you've had cancer in the past, and this is correlated with in the future. And so an employee, so if someone wants to hire you, they might say, well, because they have a history of cancer, they're less likely to be able to stay at this job a long time. And these sorts of things could come up with possible employers. So, this is something that you might not want to be public, right? This is quite reasonable. That's kind of a hard consequence, whether you are given something for like hiring. It could also be that there are other questions of whether your health insurance should be able to charge you more or not if you have these, say, a pre-existing condition or something like that. And there are also things about should this be a private matter or not. These are kind of grayer areas, but I think like choice of employment, could be possible a direct consequence of this. And this seems like, from your perspective, if this is your data, then this could be unfair, right? So but this was not always clear, right? So let me go through an example of something that happened. So in I think the year 2000, so the state of Massachusetts was trying to be very forward-looking on this, and there's lots of universities in the state of Massachusetts, and they probably kind of lobbied the legislature saying, think of all the science we could do if we knew everyone's health records in the state. We can make predictions, provide better health care, and stuff like this. And so the state government decided to release all of the this should be states, all of the states and all the medical records of the state's employees. All right, but but they said, we're not going to tell you the names. We're going to wipe all the IDs or give them kind of a ID that doesn't link to them in any specific way. But so you can do spatial geographic analysis. We'll give you things like the zip codes. We'll give you the birthday and the gender, so you can try and make links between these sorts of things. And so the government said, okay, the data has been anonymized because we're stripping out the name and kind of other specific information which could obviously identify these people. But at this time, and this is still true in a lot of places, in Massachusetts, it was possible to buy voter data, and I think this only costs like $20. And it said of everyone who's voted, it doesn't say how they voted, but it said if they voted, and it had their name, but also their birth date and the zip code. I think it may have also said the gender up there. And so it had this other information, right? So it's not exactly the same as before, but in some cases, so you could try and take these two data sets and join them together. And so there was a graduate student at the University of Massachusetts who decided to take these two, and she joined them together. And for not everyone you could figure it out, but in the case of the governor of the state, at least this is the story I've been told, is you could identify the governor based on this because of the zip code that he was in, and his actual birthday kind of actually narrowed it down to just the governor. And so the story, she mailed the health records of the governor to himself as a way to demonstrate that this may not have been a good idea, right? So she now teaches at Harvard. This was the start of kind of a career in trying to understand these issues. If you just strip IDs, there are these other data sets out there that have other information that you can match the name with and identify people with. Okay, so just stripping IDs is not a good way of determining privacy. So that's kind of the first thing I want you to try and get. So hopefully, if you learn nothing else, just taking the names off a data set probably is not enough to keep it private. Okay. So after this was kind of it's like a pretty interesting event. People started talking, what can we do to try and protect privacy more? And so the idea was to try and modify a data set D to D prime, so that hopefully analysis on D prime is still meaningful. But you can't identify individuals. Okay, so this is the general goal of what we would like to happen. We'd like to kind of modify the data set to some D prime in some way so that it's anonymized. And the simple idea was just stripping off all the names, right? We stripped off all the names. Then, we didn't need to know the names to do analysis on it. But we can do other sorts of modifications. We can remove other sorts of data that might be identifying, right? So, and hopefully this is still enough to do some sort of analysis, right? So how can we change? So the question is, how can we do this change? And so the first few approaches try to, so that this change from D to D prime was to remove data. So to just try and remove data so that in some ways, so you couldn't, you could no longer identify individuals. And how little data could you remove up to some sort of standards. And so what happened is there was this evolving set of standards of what was the right property to have in some data set D prime so you couldn't identify individuals, right? The issue with the governor in the previous example was that by just looking at the zip code, the birthday, and the gender, you could figure out exactly which record had to be the governor's because there was only one health record that had those traits. So if you found another data set that had those same traits, then you could positively identify it was the governor. So the first kind of approach to this was called k-anonymity. Okay, and so for an idea here was that for each set of kind of unique, so public traits in D prime, there are at least k data points. So okay, so the idea is that I'm going to remove information from D to get down to D prime so that I never have fewer than k. You can set k could equals 10 or something like that. 10 data points I have this exact same so public information, right? So this could say, and maybe the simplest way is just to remove information. I'm going to remove the birth date on a subset of the items, right? Because the birth dates are so pretty unique identifiers. Or maybe I don't say that instead of the day, the month, and the year, I can remove the day. So I just have the month and the year of the birthday, right? So I have lower resolution. Maybe instead of just the zip code, I say here's a set of 5 zip codes which are similar. I'm going to map them all to the set of 5 zip codes instead. So I'm going to kind of try and remove information so that for every data point, there are at most k-1 other data points that have the same values in the public traits, the ones that we believe could be matched with these other sorts of databases. Okay, the private traits with the cancer and stuff like that, that's private anyway, so we don't think those should be matched, right? You have to define these public and private traits here. So this turns out, so this is still used. So this is not too far. There are other issues on top of this, but with like medical records, this is one of the things that's used. There are often standards that look so that look like this within the release of medical records. There are other certain even more sensitive things that they don't let you release at all. But this is one of the standards used. We've had projects done in this class in the past where people have gotten a data set and then later realized that it had been transformed to follow this policy with k equals like 100 or 1,000. So they had all these data points that had all the same kind of attributes in a certain set, so they were all assigned the same like spatial location. when they, instead of saying it's in some region, they just gave them a precise location, but it was rounded to a single point, when they thought they were getting much more precise information at the start of it. Right? So something like this is still used. And also in my teaching evaluations, in my courses, if I have a course with fewer than I think like 4 responses, then I don't get any individual parts of like the feedback back, or I don't get I get something at a much higher level of the summary in the feedback of the course. So if I teach a small seminar or something and less than 4 people respond, I don't get feedback, right? So this sort of idea is used still in a lot of places. But what could possibly go wrong here, right? So this is not a catch-all. This doesn't solve all the problems. If I wanted, thinking just with health records and cancer information, what, for instance, what could possibly go wrong?
Well, let's say that K was 2 and you only have to look at 2 different health records or 2 possible people. You can easily iterate over a small number of people at test.
Yeah, so it could be I'm down to a small number. Maybe I can set K to be larger. Say I can set K equals 10, but I say one of these 10 is the governor's, right?
Yeah, if the traits are similar enough, people might look at it and try and just guess like a possibility, like, oh, maybe one of these people has Alzheimer's. People start guessing that the governor has Alzheimer's just because he has similar data.
Yeah. So it could be. So there's like so it still could be. Oh, didn't need to do that. Still could be like 1 out of K chance. So correct. But one issue that actually could happen, maybe this won't always happen, but you could even have that maybe all K have cancer, right? If I identify the governor down to 10 people, what if all of them have cancer, right? This might not happen, but it could be. Maybe it's only 1 out of 10 chance they have cancer. But what happens if you happen to be in a subset where everyone has this trait that you wouldn't want to be revealed, right? It's still kind of, it doesn't protect against this case. Oh, okay. So great. So after this, people wrote some other papers, and there was another standard proposed called L diversity. Okay, and it says that it still is the issue that if you're in a group of, this basically starts with the K anonymity, but then says there are like L like classes. So let's say L equals 2, and there's say cancer and no cancer, right? And so what it says is that each kind of set of greater or equal than K must have at least 1 in each class. So what it's saying is, so in the example with cancer, there must be in each kind of set of K things, at least K things that have the same traits, there must be at 1 with cancer and 1 without cancer. So what this leads to is maybe like plausible deniability. So you can say something like, well, someone in this class, sure, I might have cancer, but I will swear publicly that that this record is not mine, right? So if you were trying to do hiring based on this, you said, okay, maybe there's a 1/10 chance that someone has cancer. You know, I can't really make a decision on that. That's a small enough. It's a small enough chance, right? And so with a politician, they can say, oh no, this, you know, they can publicly claim that's not theirs, and what are people going to do about it if they really are protected, right? So, but as you're saying, like this partially solves the issue, but it's not great if, say, so say like, what if k minus 1 out of k so have cancer, right? So if all except one of them have cancer, this satisfies this property, L diversity. There's at least plausible deniability. There's one in there where someone doesn't have cancer, but you know, if this is like 90% chance they have cancer, right? So this could still happen under this constraint. I have some deniability, but it's not perfect, right? And there could be a case where I still 9% chance you have Alzheimer's, you have cancer, you have something like this, and someone's willing to say, okay, I'm not willing to take the risk because of like the chance of this diagnosis is high. This does not protect against it. All right, so then there was kind of a third thing called so closeness. So and what this says is it starts with so k anonymity, and L diversity, but it says that the so distribution of the private so traits must be T close to all data. So I look at some distribution and I use something like one of these distributions between these probability distributions or something like that. I think they used Earth mover's distance is what they used here, but you can think of it like the Kolbach-Liebler divergence or something like that. Could be used in there. And you say that it must be close to the population data. Doesn't need to be exactly the same, but it can't be too far from it. So I could say, okay, I can't get this property because if 90% have cancer, when really the population has only 10% of people have had cancer, well then this would be too far away. So this is, I can't release this data because it's too different from what the baseline would be. Whereas if I was fairly close, let's say 10%, and it was 2 out of 10 had cancer, well then I could say, well, you know, that's pretty close to the average rate, right? So you shouldn't be concerned because the rate is not that much different from what the average rate in the full population is. So this is a more stringent kind of policy that you can release data in so in this way. But if you think about what's happening, if I go from k anonymity to L diversity to T closeness, maybe more and more constraints on what I can release. And that means I probably have to round my data or aggregate the data or delete more and more of the data. And actually, if each region has to be close to the baseline population, right, the all data, then there might not be many interesting patterns left to actual mine after I've done this. It looks like, okay, there's no structure in the data because everywhere it looks like it's going to be close to the average data, so I can't do any fine-grained analysis anymore. There might be some I can do, but I've really reduced this amount, right? So kind of, and so I've picked out kind of the 3 most prominent approaches in this line of work, but there are probably like a dozen other variants of these that have that have come along. So 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 and so so and this doesn't kind of and this works with releasing, like this is describing like releasing data sets, but there's kind of these other sorts of questions you could ask, right? Let's say I have access to a data set and I'm trying to describe some properties of it, which by itself does not seem like it's going to give away any information. You know, but I might accidentally do that, right? So so use that as an example. So how tall is Sylvester Stallone? So does anyone know how tall he is? So this is actually not clear what the answer is. So he actually, I believe he keeps this as a secret. I don't think he's that tall, but you might not notice that. So from movies, he'll often, I believe, he'll stand on things when they're shooting. He'll wear shoes with platforms. I've even seen a rumor on the internet that he had surgery at some point so he became taller. There are pictures, there's been websites with analysis on this where earlier in his career they show him standing next to someone, showing small, with bare feet or something, and later on, after some surgery he had, that he was standing again and he appeared taller in the afterwards, right? So his height may have changed over time. So it's not clear what his height is. But let's say I'm his doctor, and I accidentally said something that Stallone is the height of an average New Jersey man, right? So I'm not saying what his height is, but I'm comparing it to this other information. Say I'm a doctor in New Jersey. I saw him. He's the height of an average person I would see, and maybe you're implying I have an average person in New Jersey. But then you could also have, if someone was really serious about this, they can get this outside info and say the average New Jersey man is going to be 5 feet and 8 inches, right? So if I have this other information, I can do something about the first, right? It may not be clear that it's giving away something precise, but this information, any information you give might kind of leak out by looking at other sources. Maybe the doctor doesn't know what the average height is, but someone else does, and you can get this information. So how do you protect against, so things like this, right? So it's not clear. So let me give another story. So who's heard of the Netflix prize? This is a bit old now. Okay, so this was back when back in 2006 when Netflix as a company was actually fairly different than they are now. They're still about movies, but they would, I realized this year I actually have to explain what Netflix was in the past, but they would actually, they would mail you these DVDs. There wasn't a streaming service, and they had this, I think they may still have this option, I have no idea, but they had this huge collection of DVDs, much bigger than their catalog online, and you could get basically any movie you wanted, much more than Blockbuster. Remember Blockbuster? That there might be one store left in the country for Blockbuster. But they used to be dominant, and Netflix came along and kind of destroyed them because their selection was bigger. Okay, and so in 2006, and one of the things they started doing, I think more than Blockbuster was able to, is they started collecting information on what movies people watched and you would rate the movie whether you liked it or not when you return the DVD. So they had these this data set where they had these user IDs, what movie they watched, and then they had a date of the score they gave on the movie, and then the actual grade, the score they gave on the movie, right? And this was a very sparse, incomplete data set, which the matrix completion kind of stuff we talked about on Monday. Like a lot of those algorithms came out of studying this particular problem. They also had another data set, D2, where that they released that had the user ID, the movie, and the date of the grade, but they didn't give the actual grade. And they asked researchers to try and predict the grade on this data set D2. Okay? And so there was and they had another third data set that they would finally kind of evaluate the grades on, which they didn't release anything out, but you would send in an algorithm and it would give back a score. And so there was this. They released this data set and said, we'll give $1 million to the first team that can improve our rating by I think it was 10% over the algorithm that they had before. And so this kind of was one of the first issues like this. So if you're on like the Kaggle website, if you've seen that, where there's a lot of data sets released in this model, some have prizes with them, others don't. But this was kind of the first big challenge that a company put out, and put out a big $1 million prize. And this created lots and lots of research. There are teams from all over the world competing with this, and I think they gave like a 1-year deadline, and I think they got to eventually teams combined forces to try and get this, and I think they got to 9.7% improvement, and they didn't quite get it, but they got very close. There's a lot of cool research, not just in matrix completion, but also in kind of these ensemble learnings, because all these teams had different algorithms, and they kind of figure out how to put them all together to make one better prediction. So there's lots of cool stuff that came out of this. Fortunately or unfortunately, it's also true that a lot of the people also rated movies on IMDb. So most of you probably use IMDb to look up information about movies, who's in it, and stuff like that. But there's also a way you can, for a bunch of users, would log in, and they would rate movies on this website too. And so they would do it. They would have a user ID. They would have a timestamp of when they rated it, and most of them had user profiles with their actual names on it. This wasn't every user, but the ones who are really big movie enthusiasts, would watch lots of movies, would be the ones who would be on IMDb, and those would probably also be the people who thought the Netflix DVD collection was this awesome idea. So some researchers were able to show that a link between these similar data sets. And the kind of the insight was not just what movies they watched, because as we discussed, there's kind of this smaller latent space and people tend to watch similar movies, but because they gave the time that they rated them, this was a pretty big clue. If you happen to watch these movies in you post the review on IMDb and Netflix probably around the same time. And so they could identify lots of they were pretty successful identifying, so they believe they said, we think we, with very high accuracy, can identify a lot of the people in the Netflix data set. So maybe you watch some embarrassing films, like you're embarrassed, say you like high school coming of age movies, but so you would watch them and rate them on Netflix, so you would get good recommendations, but you might not post that on IMDb, so I don't know. So some people were upset about this, and there was a class action lawsuit actually filed against Netflix. It was later dropped, but the unfortunate thing about this is Netflix had proposed a sequel of this challenge, where they had a much richer data set they were planning to release. another huge, very large data set, which would have been great from my perspective to want to do research on this as a cool, kind of very cool data set. But they ended up not doing this because of this lawsuit. So because of that, it kind of, they didn't get, so Netflix benefited from this a lot. They got a great recommendation engine out of this. That was much better than the simple approach they had before. And $1 million is much cheaper actually than hiring a big team of data scientists to do this. The amount of effort put into this probably was, you know, I know the one of the prominent teams was 3 senior researchers at like AT&T Research. They spent a year on this. They probably had combined salaries of, you know, at least a third of this, at least a third of $1 million, probably more than that. And that was, they ended up being one of 3 or 4 prominent teams that joined together at the end, right? So they probably got a lot more out of this than they could have with their own R&D team. But this sort of prize is not very common anymore, this network, with this sort of data because of these issues, because you can relate these data sets, you know, so to each other. So, okay, so this was kind of around 2000, there was kind of some like despair around this, but kind of starting a little bit before 2000, I think again around 2006 or so, this started coming out, this idea of differential, so privacy. So this is kind of probably the most modern view of this, and this took a long time to be accepted as kind of, at least in the research community and in the tech companies, when they care about this issue, as kind of a useful way of like dealing with this. And so it's there are certain kind of actual algorithms, or what they call like mechanisms, to try and ensure that you have this privacy. But differential privacy itself is kind of a formal statement of the goal, and there are certain cases where this is actually attainable. Whereas the k-anonymity was kind of a looser statement of you know, I think this having k data points that have the same public attributes seem like a proxy for a good thing. But it doesn't actually say anything about what the privacy is, because you can link it with these other data sets. So differential privacy is a way that tries to get around to prevent, even if you link it with another data set, you should not be able to get too much information out of something that's released, or even doesn't have to be released if the data could be stored this way internally. I think like 3 or 4 years ago, Apple started storing their data internally using some form of differential privacy, for instance. And the US Census releases some data using various forms of differential privacy. They've decided to do this so as well. And this is becoming a more common kind of internal standard. So protect against an accidental breach of data. If it's been anonymized some way and has differential privacy properties to it, then hopefully it doesn't matter as much if it gets leaked out in some way, even accidentally. Okay, so this is basically a trait of two data sets. So I'm going to try and explain this, and I'll go through some examples. It's a bit, there's more to grasp all at once than with the k-anonymity. So I'll try to explain it and go through some examples. So there are 2 data sets, D1 and so D2. And so the goal is to say that D1 and D2 have so that D1 and D2 have somewhat similar statistical properties, meaning we can do analysis on one of them, and the analysis will be similar as if we did on the other one. So I can do analysis on D2, and I can, and I'm hoping it's similar to D1. And the idea is that maybe D1 is the real data set, but I have access to D2. So if I do my analysis on D2, then I want this analysis to be good. And so I'll describe this with particular analysis in mind, certain sort of operations I can do. But with the rule that so for any data point in D1, I cannot know it's a value, say from D2, right? So I have two similar data sets, D1 and D2, and for any data point in D1, I cannot infer something particular about its value by just looking at D2. A simple thing is, I don't know if this data point, which is in dataset D1, I don't know even if it's in there. For instance, there's this dataset that's been released about movie reviews, okay? And if I was someone who reviewed movies on Netflix, I cannot determine if my review was in this dataset or not, right? So not only do I can't reveal that this was my review, but I can't figure out, or no one can figure out if my review was actually in there. Right? If I can't figure out if it's in there, then I haven't gleaned any information about it in some way. So, okay, so as we've seen, this is kind of hard to, this is kind of, again, the broad goal here. The technical way to describe this is a little bit more complicated, and I'm going to give you kind of the formal abstract version, and then we'll go through some kind of simpler examples. So I'm going to be allowed to, so I'm allowed access to D1 or D2 with a query queue. Okay, so if you think of a database, I can issue a query, but think of this query as I want like an average value or of some trait, or I want how many people live in this kind of region, this set of zip codes. I want the total number of people, or the total number of people who have cancer in here, right? And so the two data sets are not going to have the same value, but I want that for any, so for all query in some set of queries I can ask, that the probability of the query on D1 follows some sort of event E divided by the probability that query in D2 satisfies so the same event. I will say the ratio of these probabilities is going to be less than epsilon to some error e to some error parameter epsilon. Okay, and the way to think about this is 1 plus epsilon. Okay, so let me annotate what's going on here. This is an error, so parameter, right? So the smaller I make this, that means that my statistical analysis on these are going to be similar, right? So the smaller the epsilon, the stats are going to be more similar to each other, right? So I want epsilon to be small, so my statistical analysis is better. But at the same point, I want, and this is describing some sort of event I want to detect. So the difference between the events and the query, the broader the sort of query, the query set and the events, then the more I learn about, say, D1 by looking at D2. Right, so if I can ask more and more complex questions or more questions of the data set on D2, and I know it's close here, then I'm going to recover more information about about D1. And so this is kind of, if you look in, so I'm trying to explain this because this is the technical definition you'll see in papers and on Wikipedia. So like if you look these up, this is kind of the trait you want, and you want to think of these two data sets as being, say, off by one value. Say whether my data point is in there or not, or whether I've changed the value of my data point. So let's say I have maybe I'm in there, but I changed the trait of mine, whether I have what my height is. I said I'm actually 6'5" in the data set, and so am I able to still ask something about, does it change the average height of the things in the data set by a small amount? Then this is okay, right? All right, so let me try and go through like a concrete example. So, okay, so before I go through examples, I want to say there are two main types of some mechanisms. Okay, so there are two main types of mechanisms. One is going to be interactive, and so this means that D1 exists, and I can ask queries to some sort of oracle, and they return answers. Okay, so the idea is that there's like this data set D1, and there's this firewall, and so there's this user out here, and they issue a query, and it returns an answer for the query 1 on this data set D1. Right, so this is the hidden data set that has all the information, and I can return an answer, and but usually instead of returning the exact answer, I can return some different answer as if, which is going to be equivalent to the query on D2, some unknown D2. Okay, so I don't ever actually create I could have a replacement D2 out here, and then I just give answers by issuing the query on D2. But the advantage of this is I don't need to decide what D2 is at the start. Okay, so I can give an approximate answer, and then if someone starts answering, okay, I want to know the cancer value in this zip code, and then I do, right? So think of that there's actually, so there's one person I want to identify here. I ask this range, and then I ask this range, and then I ask this range here, and this range, and this one, and by subtracting the differences between the ranges, I'm left with just what's left in this one spot. Right? So if someone starts trying to zero in on an answer, I can start deciding how I'm going to reply to these answers like dynamically, interactively. And this gives more power, and I can give more accuracy in this version than if if I first set D2. If I first set D2, I can't give as much accuracy. I have to add essentially a lot more noise into how I store D2. Otherwise, it gives me less power in some way. And then the other version is the non-interactive. And so this is, I go from D1, I basically add noise typically, or I do some sort of transformation onto it, and I do D2, and then I release D2. Right, so in this example, what I would do is I would take this and I just give the user, and I release this data set publicly. Here's data set D2, go and work on this data set. I've done something to it so you can't tell any individual data set if it's in there. I'm pretty safe, I'm pretty sure about that. But I'm probably going to have to do a lot more transformation on this data set D2 before I throw it across the line. Because I know then people can ask as many queries as they want about it. I can't control that anymore. Okay, so there are these two different kind of ways of doing these mechanisms. Okay, so let me first describe this non-interactive version. And so this is the simpler version. So that so this is often known as the Laplacian mechanism. And so this makes sense if data set 1 is going to be these values up to xn, and each x is like a real value. Okay, and so for instance, it could be, an example would be like someone's height, right? And so what I would do is I'd be D2 is going to be x1 prime, x2 prime, xn prime, where xi prime is going to be equal to xi plus so some noise, and usually you add so Laplacian noise. Okay, and so this Laplacian noise is equal to c times e to the negative epsilon. Right, so if you remember, there's Gaussian random variables and Laplacians look like this. So it looks kind of like a Gaussian distribution, except this is pointier because I'm not, if I squared e, this would look like a normal or a Gaussian, but this is, you don't square it as Laplacian. Turns out this is the right thing to do. I could have added Gaussian noise and I can get other guarantees, but typically the Laplacian seems to give the most sensible things to do. So I'm just adding this Laplacian noise onto each of these values. Okay, and then I release this with this sort of Laplacian noise. Okay, and so if this is true, I can have guarantees, something like, and let's just look at one data point here. So I want to say the probability that, say, x1 in data set 1, right? So if this is greater than 70, so let's say I'm saying this is height, this is in inches, and this would be someone who's like 5'10". So is sliced alone greater than 5'10"? This maybe is the true value, and you've released the value x2 in D2, or x1 prime in D2, and I want to know if this is greater than 70. Okay, and so let's say, for example, that the true value is going to be 68. Right, this would be 5'6". Wait, so no, 66 would be, so let's say the true value was 66 inches, this would be 5'6", and let's say I released a value that was 67. Okay, so the probability, because I know that, all I know is that the true value here was described by a Laplacian distribution, basically with standard deviation described by epsilon. So then this is going to be equal to, my pen just ran out of juice. Let me see if I can recharge it for 30 seconds. So this will be equal to e to the negative, so epsilon each of the negative epsilon to the each of the negative 4 epsilon. This will be each of the negative 3 epsilon, and the ratio of those is going to be e to the epsilon. Let's see if this worked. All right. You have a pen? Okay. Sync this quickly. Okay. Great. So this is e to the negative 4 epsilon. This is e to the negative 3 epsilon, right? Because the distance is 4 here, and I know that the error came from this distribution, so the probability that it's greater than 70 turns out for the Laplacian distribution is going to be e to the negative 4 epsilon, and this is going to be e to the negative c epsilon. There might be a coefficient in front for normalization, but that's going to cancel out. Maybe there's a c in front here. And so this is going to be e to the epsilon is going to be the ratio, or maybe it's negative epsilon here, and this is going to be roughly 1 minus epsilon. Right? So if it was in the other direction, if this was 60, 65, then this would be a minus 5 here, and this would be positive epsilon. It would be 1 plus epsilon, right? So the probability, if these differ by 1, if I change the data set by 1 here, I can't tell within a 1 plus epsilon probability roughly whether his true height is off by an inch if I have this Laplacian mechanism. Right? So that's roughly what's going on. This is one simple example. Okay, so let me give one more example, and this works with this interactive version. So database. Okay, so now I want to say that I have some data set D1, which is just going to be a, which is just going to be a like a bit vector. Okay, so it's just a bit, and D2 is going to be another database. Okay, and I'm going to have the guarantee that the Hamming distance between D1 and D2 is going to be equal to 1. Have this guarantee, which means that their bit vector only differs in one of the values. Right? This one is 1 and this one is not. So think of this now as something like, is your data point in this data set? Did your review or your set of reviews get into this data set? It's 1 if they're in there, it's 0 if it's not in there. You could also think about it as this is a data set. Do you have cancer or do you not have cancer in the data set? So I don't, and that's described by this one by this question here. And so now I'm going to say I'm going to ask some queries from this thing, and I'm going to say that so this is defined so that each query is going to be an XOR. Right, so I'm going to add up. So basically, so Q is going to be a bit vector, and I'm going to be the XOR with the bit vector. So this will imply that I'm actually doing. It would be I have a data set. I'm going to do an XOR with Q, and I'm going to return the count. Okay, so an example of this would be a Q would be so what this is going to do is that it's going to look at the values where there are going to be 1 bits, and I'm going to count the number of 1s that align with the 1 bits in the query. So I can select any subset of the database, including just a single bit, for instance, and I'm going to ask how many 1 bits are in there. So I can ask the query, all the people that satisfy this constraint, how many of them have cancer? Okay, so so a query is equivalent to how many, say, people in some range have so cancer, right? So it can be a question like this, and the range is defined by where these 1 bits are, right? So this is a very powerful class of queries. All right, and so what the way this works again is applying the Laplacian mechanism, but only applying it on the answer of the query, right? So what I'm going to do is I'm going to return. So if I ask, so how this will work is I'm going to have some data set D1. There's going to be this barrier here, and I'm going to have a user. He's going to ask a query. What I'm going to do is I'm going to calculate the query of D1 plus some Laplacian noise. And I'm going to send this back over as the answer of D1 and the query. Okay, so I'm only going to send back the answer. And so this guarantee works for us for asking just the simple version of this I want to show you is that if a user is only able to ask a single question, I can guarantee that error that I can protect whether your information is inside the data set. Right, so let's go through this analysis. I'm going to have the probability that the answer from data set 1, Q equals X, versus the probability that the answer of some D2 of the query is going to equal this same value X, right? And I'm going to guarantee that the Hamming, I don't know what D2 is, but the Hamming distance by D1 and D2 is only equal to 1, right? And I'm looking at the ratio of these two things, and this is the answer you're actually seeing is going to be X minus the query of D1. So if I think the answer is D, that I'm going to add like Laplacian noise onto here. Okay, and so what is this going to look like? This is going to equal to e to the power alpha. This is epsilon. Say epsilon times x minus the query on D1 minus x times the query on D2, right? And this is less than e to epsilon times the difference between the query on D1 minus the query on D2. There's some absolute values in here, but it's no worse than because x is the same. Is it actually this value that I'm seeing? And so I know that the difference in the queries is going to be less than 1 because of this, then I can say that this is less than e to the epsilon, because I know that this term is going to be less than or equal to 1, and this is approximately equals to 1 plus epsilon. Right, so I'm going to have the probability that if I get some answer after I've added Laplacian noise onto it, so let's walk through what this means. Let me try and explain this. Is that so? If I have 2 data sets and I return the answer x on data set 2, right? So if this is my observation, right? And so so this is the observation on R. Okay, so how many people in this region have cancer? And the probability that I would get this answer, let's say the answer is 7 in some region, is going to be on a different data set that was off by 1 data point, whether your data set was in there or not, was off by a factor of 1 plus epsilon. Right? So if I added a Laplacian noise with a standard deviation of 0.1 onto the count in the answer I gave, then what that means is that the ratio of the probabilities is off by like 10%. So the probability, if your data point is inside the range, that you do have cancer, or you don't have cancer, the probability I'm going to get the same answer is off by 10%. So it's this probabilistic guarantee. Because there's random noise and it depends on the random noise. Because the observer does not see the randomness, they can't say with a lot of confidence, let's say I just asked in the 1 region and the return count is going to be 1 or 0. Do you have cancer or do you not have cancer? And because I added noise to it, depending if I add a lot of noise, okay, so then the probability that these are going to be the same is going to be very small. If I have a small amount of noise, then the ratio is going to be high, right? So it kind of allows you in some tunable way to add more noise onto the data. The more noise I add to the release, the more the less analysis I can do on the data set, the more sure I can be about the analysis. But people can actually do more deduction about the individual data points. They can be more sure about them, right? And so there are certain ways that you can kind of prevent this by adding kind of noise into the answers. So this is, I'm not sure how clear this is. This is kind of, it confuses me kind of like a small amount as well. Just kind of without working through the examples of of how to use it. But these are kind of like the strongest sort of guarantees that you can make are of this form. What I've described as fairly simple mechanisms, if you do this interactive mechanism for here, where I can ask more than one query, there are ways to get similar sorts of guarantees. But I have to kind of adaptively change my answers as I go. So people have looked at, say, I want to run gradient descent, or I want to do something like SVD on the data set, or build a classifier. And to build a classifier, I need to ask certain queries about the data set. I need to interact with it in certain ways. I need to iteratively do this. And so how close can I get to the SVD or the PCA of a data set so without revealing too much information? And people and researchers have kind of figured out more complicated mechanisms to do this, but it will take, on this side of the equation, there's a lot of computational cost that has to occur here. And there's trade-offs in how much computation you need to do to answer some noise which is adapted to the set of queries you've done, so you can't recover everything. But there's been a lot of research of this over the last 5 or 10 years to make these more powerful, so you can do this. What is commonly done in places like Apple when they announce they're doing this, they're probably doing, they aren't necessarily clear, but they're probably doing something like this, where every data point, they're just adding some noise to it, and they say it's differentially private at this point. And depending on how much noise they add, it's going to have more protection. If they don't add a lot of noise, then they don't have a lot of protection, but their analysis still works. And so it's not clear how much noise they're adding onto it. So if you look at these things, you need to look at the fine details to understand whether they're actually protecting your data or not, or it's just something they're doing to try and placate people from complaining about the privacy issues. So, okay, so hopefully you at least have a concept of roughly what this is trying to do. You know, if not knowing exactly how the mechanisms work and what the guarantees are. Okay, so next week we'll start talking about graphs, and the first section will be, might be a review to some of you on Markov chains, but hopefully I'll give you a new perspective on this, because there's often multiple perspectives on this, and I'll try and cover both sides of the story. All right.